right, Alvis is on. So I originally, until this morning, I had the chapter 2 first chunk of problems due tomorrow. I just switched it to Friday because it's on the infinite square well, those 4 problems, but you're supposed to be turning in the rest of the chapter 1 stuff today. I thought it was a bit of a rush, so work on that for Friday. And we should be getting into the harmonic oscillator, section 2.3. By the way, I noticed in 2.1 and 2.2, I went to look for reading responses, and if I remember correctly, there were only 2 people. I was going to grab some things, and only 2 people had written reading responses. 2.3, 5 of you had put them up, but just don't forget about those. They're worth some amount of credit for the course, and I also enjoy sort of working in those comments every once in a while to make contact with what we're talking about in the class. Any other concerns before we sort of go back and touch base with where we were in an example problem and then finish up the discussion of the infinite square well solutions? All right, good. So let's get this up here. And the last thing I think we talked about was an example problem. So this is on a worksheet for which I think you had done the front side of the worksheet, but we haven't looked at the back side of the worksheet yet. And through sort of a mess that I talked through quickly, when you calculate the expectation value of energy, remember that means sandwich the total energy operator in between psi star and psi and integrate. That was the formalism we came up with for any dynamical variable. Certainly the total energy is that. And when you work it out, all the details, and use orthogonality of those wave functions and whatnot, stuff that Griffiths has proved, you find out that it's of this form. The expectation value of the energy is the sum from 1 to infinity of the magnitude of Cn squared. Remember, those Cn's were whatever at time t equals 0, we're going to take whatever shape we say is our initial condition or initial shape of the wave function, and we're going to write it as a linear combination of these psi n's. We're treating them like basis functions, just like you would write an arbitrary vector as a linear combination of x hat, y hat, and z hat in 3 dimensions. And we talked about how to find those Cn's, and in this case, you can show that the expectation value of energy is the sum of the magnitude of Cn squared times En. And this is perfectly general. It doesn't have to do with any particular psi 0 or anything. This has to do with any kind of problem we could write down. So if we write that down and compare with what we figured out in chapter 1, the expectation value of H can be written as the sum from 1 to infinity of the magnitude of Cn squared, En. And remember, back in chapter 1, we said if you have a discrete variable, like the example with the average age in the room, we said we could calculate the average age in the room by summing from overall ages. Let's start at age 1 or something like that. The probability of I guess we'll call this n, the probability of age n times that age. So here we're saying the probability of the expectation value of energy is the sum of something times the individual energies. It seems like this might be an expression for the probability as a function of energy. In other words, this is going to be something that is 0 everywhere except at a value of En, and then the magnitude of Cn squared would be the probability of energy measurement yielding the value En. let me go back here and fast forward in the notes. So here at this point in the book, Griffith states, and if my memory is correct, he sort of makes it sound like it's obvious, but it's not obvious. The evidence is something like this. If you can show this, it kind of seems like this might be the probability of a measurement of energy yielding the nth energy eigenvalue. The probability being 0 for any energy value that's not an energy eigenvalue. This you can't prove yet, and we're going to introduce it as a more general postulate in chapter 3. This is a little bit out of order of the notes, but it's on an adjacent page there. But it's really telling us, you know, if you can expand your initial state wave function as a linear combination of definite energy functions, this tells what the probability is of an energy measurement as a function of energy. And you can think of it as we're sort of figuring out what rho of E looks like as a function of E. And we're saying, you know, here's one E1, here's E2, here's E3. They're getting farther and farther apart on the x-axis. The probability is going to be 0, 0, 0, 0, and then there's a finite probability for that, and a finite probability for that, right? And so on. And what those probabilities are, how the probability of measuring E2 relative to E1 is, depends on what state you're in. It depends on the relative size of C2 relative to C1, and that depends on your initial state. Okay, so that's something we'll make contact with, but I just wanted to warn you that Griffiths, if I remember correctly, just makes it sound like it's obvious. Now, let's go back to the problem that was on the first page that we were working through there of that worksheet and remind ourselves what those CNs are, and then we can sort of think about something, and we'll see that there's a little bit of a surprising problem here. We started out with this wave function, which I gave to you to make the integration easy. So it was either 0 everywhere, including outside the well, but 0 through half of the well, and then it had a constant value through the left half of the well. That made our integrals easy. We said now, after the last part of the problem, this is how we can calculate the expectation value of H, and earlier on in that problem, we calculated the CNs, and here they are down here. This is the first 5 of them anyway. C1, C2, C3, C4, C5, and so on. They are actually getting smaller as the series goes up because of this n in the denominator. The denominator is going to keep getting bigger and bigger and bigger as you go out. So you might hope that this is a convergent series, but anytime you have an infinite series, you got to worry about, well, does it converge or does it just keep going off to infinity? And in this case, this particular series is divergent. It just keeps getting bigger and bigger as you add more and more terms there. And so that's a little bit concerning. We'll talk about that later on. It comes from the fact that the initial state that I chose, which was made to make your life easy, it looks like this. Here's our infinite well, here's 0, here's A. Our initial state was constant until you get halfway across, and then it goes back to 0 again. That was the shape of psi at time t equals 0. And notice we've got discontinuities or very sharp edges there. And you're going to find out every time you have a discontinuity or even a kink in your initial wave function, for discontinuities, you're going to find the energy, expectation value of energy is going to be divergent. And if you have a kink in it, the expectation value of momentum will even be divergent. And what that's indicating is that, well, this probably isn't a really physically realizable wave function. If the expectation value of energy is divergent, that means it's kind of like infinity. That means I kind of, to prepare this state as the initial state, I would need an infinite amount of energy, right? Because I've got to put in enough of those high energy states as linear combinations to make the whole thing, to make this really sharp edge here, that I would have to have an awful lot of energy around, an infinite amount of energy. And so I probably can't produce this initial state, even though there's nothing wrong with considering it. It's just that we'll get some divergent quantities. Okay, so that's a little bit of a warning there. So to avoid that, here's an example from Griffiths, and I'll just sort of flip through it that I rewrote in the notes. But Griffiths is avoiding that by saying, okay, here's our well, 0 to A. It's 0 out here. Let's not have it be discontinuous. Let's take a piece of a parabola that goes up and goes down. We'll normalize it, but then it won't be discontinuous. And then we should find that the expectation value, if you believe me here, the expectation value of energy is perfectly finite. So analytically, that, it's a parabola, so it's a quadratic form function. It's got to be 0 at x equals 0 and 0 at x equals a. So that tells you this is the factorization of that parabola. That's at least between 0 and a, 0 outside of there. And when you go through the trouble of calculating the CNs, here's what you have to do, right? Remember all of this takes a lot of memory or doing over and over again, so you know what to do. Here's our lowercase psi n's, right? Root 2 over a times sine n pi x over a. That's psi n. We're putting next to it psi of x at time t equals 0 and integrating from minus infinity to infinity. And then we're saying, well, it was 0 everywhere, so I can reduce the domain of integration from 0 to a, except to where it's non-zero, and then I can plug in that formula there. So that's how we calculate the CNs. And if you just want to do this, you did this kind of stuff way back in calculus, right? This looks like integration by parts. What I would first do is distribute this. So I get a linear term in x and a quadratic term in x, break it up into 2 integrals. So I would have an x times the sine of stuff, and then I'm also going to have an x squared times the sine of stuff. And those are integration by parts kind of integrals. Well, it still doesn't matter because functions of x always commute with each other. So if I have an integral of psi star, and in this case, again, psi is real, it's a sine function, so the star doesn't come to anything. And then sorry, that should be a lowercase psi. And then here I have my initial condition. Doesn't matter which order I write functions in. It's when you have operators that are taking derivatives, you can't willy-nilly switch them around, but functions always commute like that. So yes, I'm not really thinking too hard about it here. Good question though. All right, so we do that. I didn't show the work here. Here's the results. You can see Griffiths does this exact example, if I remember correctly, in the book. Here's the formula as a function of n. So this says we've done all the integrals as a function of n, and then we can sort of interpret a little bit more to get an idea. And so what we're seeing is all the even n values are 0. So Cn is 0 when n is even. And then the odd ones are non-zero, but they keep getting smaller and smaller pretty quickly. They go like 1 over n cubed. And when you sum from 1 to infinity, 1 over n cubed, that's a perfectly convergent kind of p-series integral. I think those are called, right? The power, inverse integer powers of the summation variable. So that's something that, you could at least see that it's convergent, even if you can't analytically get the expression for what the expectation value of h is. Okay, so therefore, again, just to put everything together, we had an initial condition. It looked like this. Now I want to write down the full time dependence. So what we do is write down the sum. It's kind of hard to see because there's such a mess in there, but let's write it in symbols and then we'll go back to the screen. We're going to write psi. We write psi of x and 0 as the sum from 1 to infinity, Cn times psi n of x. Those are our sine n pi x over a kind of functions, right? And then to put in the time dependence, what we do is just put in the corresponding negative exponential Ent over h bar. Okay, and what I was showing here is just that with stuff in this particular problem substituted in. the lowercase psi ends are sitting, oh, that didn't look good. Lowercase psi ends are sitting right here, right? This is part of the CNs, the constant part of the CNs I factored out in front of the sum. We realized that the CNs were 0 for even ends, so I just put odd things in the summation just to be efficient about it. And here's those corresponding exponentials. And the ENs correspond to the ENs, you know, that's the formula that we gave for the infinite square well. Okay, and again, since 1 over n cubed, those CNs get small really fast. This thing doesn't get small as a function of n, but the 1 over n cubed gets small fast, and therefore these terms are getting small sufficiently fast that you could maybe just keep the first 5 terms, and you'd get a pretty good approximation to what the wave function looks as a function of time like. Now it's complex because that last factor is complex, but it's going to be moving around and wiggling and jiggling in the complex sense as time goes on. And if you don't like infinite series, just keep the first 5 terms of that, or maybe even the first 3 terms would be a good approximation. And if you look at time t equals 0, it should be a pretty good approximation of your initial state. Okay, questions on that Griffiths example? Right. So again, just to add on to this, looking back, so we've made the statement that the magnitude, or Griffiths is claiming, and we're going to assert this as a postulate in chapter 3, the magnitude squared of the CNs are the probabilities of measuring ENs. Now, just like the probability of a position measurement better be 1 when we add over the whole x-axis if something is confined to the x-axis, right? The particles, by definition, got to be somewhere on the x-axis. If there's only these discrete values allowed of energy, when we measure energy, it's got to be one of those infinite number of allowed energies that we get. And therefore, when we add up the probabilities of all those different energies occurring in a measurement of energy, they better add to 1, right? And so this is sort of an aside here, but the fact that those probabilities have to add to 1 sometimes gives you you can sum some really weird series, okay? So as long as psi is normalized, if you normalize psi, choose the A to make it normalized, then they're definitely going to add to 1 as probabilities. And in this example, the CNs looked like this. So if we sum over the odd ends of this thing squared, let's require that equal 1. And then let's take all the constant stuff and divide it out onto the right-hand side. And when you do that, you find out, just from doing this example and thinking about the fact that the probabilities have to add to 1, we have proven that the sum over odd ends of 1 over n to the 6th is pi to the 6th over 960. And you can do lots of different examples like this, and you can infer some weird series like that. You know, you probably didn't encounter that series back in calculus 2 or 3, whenever you do series here. But, you know, sort of a non-intuitive series, not at all obvious that would be what this sums to, but yeah. So that's sort of a cottage industry for some people who really like analytic summing for series. They will use this kind of probability interpretation, and there's a whole formalism for generating analytic sums of series. It may not be a series that you ever really care about, but in this case, that's kind of interesting. Okay. Okay, I think we want to do these voting questions now. Let me just flip and make sure. Yeah, so I think this leads in nicely to the last worksheet problem that we're going to do on the infinite square well. Particle in a box, right? Infinite square well, size A, same thing we've been talking about. Here at time t equals 0, I'm giving you what psi is as a function of x at t equals 0. Now you got to kind of carefully inspect this. And remember the fact that the magnitude of Cn squared corresponds to the probability of a particular energy being measured. And of course, the only non-zero probabilities correspond to the allowed energies. All the other probabilities would be 0. So there's two questions being asked here, and the answers are on the left and on the right. What's the probability of measuring E1, and what's the probability of measuring E2? Ground state energy and the first excited state energy. You got to kind of look at this and disentangle the symbols and see what to look at there. We're thinking of probabilities corresponding to the magnitude of Cn squared. I'll give you a hint that there's something in it that's sort of a trick question. You really have to inspect the symbols in there to get the correct answer here. All right, let's just see about, I don't know where you guys are at. Some of you are holding up fingers or cards and some of you not. So if you've got a suspicion, just even a hunch, hold up your card. Let me see if we're all in the same place or not. I would say probably not. There's maybe one of the letters that's missing from the responses. So let's just talk about how to disentangle it. I'm looking at, I better write over here so I can make sure Alvis can see. Remember, psi n as a function of x is root 2 over a sine of n pi x over a. Okay. Sorry, I ran up against some other stuff there. So I need to look for the coefficients of those. Does psi 1 appear in the linear combination we're seeing up there? Sure it does, it's on the left. Does psi 2 appear? No, it doesn't. The one on the right is psi 3. That's what's sort of a trick there, right? Psi 2 doesn't appear in there. So this, maybe I should point here. This sign in combination with the root 2 over a is psi 1, and its coefficient is root 1 over 3, root 1/3. And this, in combination with the root 2 over a out in front, is psi 3, and its coefficient C3 is root 2/3. So the trick is, you weren't asked about E1 and E3, you were asked about E1 and E2. E2's coefficient is 0 because it doesn't appear in that series, right? So is E4's the psi 4's coefficient is 0 as well. All the other higher psi 1s are 0. You can think of this as it's an infinite series, but all the coefficients except 2 of them are 0. So it's sort of an easier to handle one. So that means because C2 is 0, C3 was non-zero, but C2 is 0, the magnitude of C2 squared is 0. And C1 was root 1/3, and we take the magnitude squared of that, which is 1/3, and that gives us the probability of E1. Probability of E3 would be 2/3. That wasn't asked about on there. That was the trick part. I stole this from somebody else. I know it's a little bit of a cheap thing with that 3 being snuck in there. You really have to kind of inspect it. So any questions about that? C is the correct answer there. Okay, let's see. Yeah, this is saying the same thing, that we can calculate the expectation value of energy now by using those probabilities and substituting the magnitude of Cn squared. If we know those Cn's, that allows us a different way to calculate the expectation value of energy. And we showed in the first problem on there that this comes out to the same thing. After a lot of simplification, it reduces down to that. That's what the last part of that last problem was. Okay, I think this really is the same case as the one so this is just written out in the notes rather than in the worksheet. But if you have a function that is discontinuous, so this one jumps, it starts out at √2/a and then jumps down to 0. I think this is the exact function you have. Then when you calculate the CNs don't get small fast enough. And when you calculate this expectation value, you get something that is divergent when you calculate the expectation value of energy, if it has discontinuities in the wave function that you choose. So, okay, there's nothing wrong with that, but you realize that it's not physically realizable. We couldn't prepare that because it sounds like it would take an infinite amount of energy to do it. Makai? Well, I mean, you've got to go back to your stuff from sequences and series where you talked about 1 over, so 1 over n is just barely divergent. So if you have 1 over n to the 1, that's divergent. But if you have 1 over n to the 1 plus even a tiny amount, that's convergent. So those are called p-series kind of series. In this case, notice this, the CNs were getting smaller, but the ENs have an n squared in the numerator, right? N squared pi squared h bar squared over 2ma squared. So this has an n dependence in it too, the EN. So I put it all in there, and the one, it looks like the 1 over n squared when I squared CN canceled out with the n squared from the EN. And then when I look at what's left besides the constants, it's some things that are just not getting any smaller as you go out. They keep repeating these 4 values. When you add them up, it's clearly divergent there. So the CNs have got to get smaller faster than that. And the problem is that kink in the function. What does this mean, just as the last comment, and then we'll do that last worksheet problem. What does this mean in terms of energy measurements? If the expectation value of energy is infinite or a divergent series, the way we're converting it, suppose I managed to prepare that state and I measured the energy of such a system. Would I get an infinite energy? Strangely enough, the answer is no. If you prepare that state that has the discontinuity in it that we've been talking about, if you measure it, you prepare maybe 1,000 identical systems in that state and you measure the energy of each one. Each energy measurement would be perfectly finite. And you would find out, maybe the first one corresponds to E13, and then you get an E50, and then you get an E25, and then you get an E436, and so on. And you start calculating the average of those, and you keep track of the average as you take more and more and more measurements. And you would find that the average keeps getting bigger and bigger and bigger the more measurements you include, and it just never stops getting big. Because at some point you're going to get an E10,000 and then you'll get an E1,000,000 some random time and all that kind of stuff. And so it will diverge that way. But each individual energy measurement is still one of the perfectly finite ENs that we have derived. Okay, so the summary is, you can think about this why in terms of derivatives, because there's this has the energy operator has a second derivative in it. The discontinuities cause problems for the expectation value of h, and the momentum operator has a first derivative in it. It's sensitive to kinks as well. So just be aware when you put those extreme kind of features. I put them in there all the time because they make your integrals easy. If you have something that's constant and then it goes to 0, we can calculate all the coefficients easily. That doesn't mean it's physically realizable. So don't be surprised if some of these expectation values are divergent. You probably won't see those kinds of initial conditions in Griffiths, but I use them a lot because they're just easy to try to do the integrals with. You don't have to think too hard. Okay, and we did that. I think we are supposed to do, let me just check my notes here, make sure where we are. Yes, worksheet number 2. So let's try worksheet number 2. That's the back side of the one that you were doing last time. And I really just want you to do parts A through C. Part D takes a little bit of working on, and I'll just do that together with you. But try A through C on that worksheet that we were working on Monday. That's on the back side. It's labeled as problem 2. It seems a little bit different because there's not an infinite series here. It's just a linear combination of 2 terms rather than having to write it as a full infinite series. And that can sometimes throw people off. Again, I have no shame in asking you to find a normalization constant every time. I got A is 1 over root 13. So you can compare to that in part A. B, I got 4/13, and C, well, we'll talk about C when we get there. Let me see. If I don't, I probably have one back in my office. I think I only brought what I expected, but let me put it up here. Oops, that's not what I want to do. Let me bring it up so that you can at least see it. Let's see, chapter 2, infinite well. Yeah, this one, I think. Oops. So here's parts A through C, at least on the screen. Anybody having trouble getting started on A? Okay, let's talk about the normalization constant. If you put the sign stuff in there, you're probably making too much writing for yourself, because we can actually just leave the size here. So I've written out what psi star times psi, we're integrating and requiring that it's equal to 1, and see what that means A has to be. And so the first thing I had to do is FOIL this out, or distribute out, so that I get 4 different terms. I'm going to take the magnitude of A squared outside. We're going to take A to be real, so we won't really worry about the magnitude part there. But when I multiply this out, I get a 4 times the integral from minus infinity to infinity of the magnitude of psi 1 squared dx. That's the first integral, right? 2 times 2 is 4. I get magnitude of psi 1 squared. Let's do the last one. Plus 9 times the integral of the magnitude of psi 2 squared dx. Now let's do outer. That would be 2 times 3 is 6 times the integral of psi 1 star psi 2 as functions of x. And then inner will also be 6 times the integral of psi 2 star psi 1 dx. Sorry, I should unshare so this gets in the video there. Okay, so all of that stuff I've just multiplied this out and then distributed over the 4 integrals. Now, what do you say about this integral here? It's 1. It already, once we've normalized it, or sorry, we know these are normalized. We've already, they have the root 2 over a in them, so they're already normalized. So this is equal to 1. This is also, for the same reason, equal to 1. Psi 2 is equal to 1. What about the integral from minus infinity to infinity of psi 1 star times psi 2? It's 0. That's part of our orthogonality property. Remember, these are like vectors. This is like a dot product, this integral. And that dot product is 0 when we take 2 of the different basis vectors. Okay, so this integral is 0. Similarly, this integral is 0. We're thinking of that as an inner product between these 2 orthogonal vectors. That's what that Kronecker delta was about. So that's kind of nice. This is 4 plus 9 is 13. That stuff over there is 0. So that means the magnitude of a squared times 13 is equal to 1. And that means a, if I want to make a real, and usually you can make a be any complex number that has the right magnitude to make it normalized. We'll choose a to be real, and that means a could be 1 over the square root of 13. I over the square root of 13 is also a perfectly valid normalization constant, but people usually leave the complex stuff out of the normalization constant because it doesn't really help anything. Okay, that's A. Any questions on that? I just wanted to show how to do it somewhat more efficiently. 1 over root 13. What about B now? Well, okay, so B is asking, find the probability that measurement of the particle's total energy equals E2. So we now know Griffiths is telling us, without so much justification, that's the magnitude of C2 squared we need to calculate. Now, what you need to realize is that I can read the C2s off of this, right? C1 is whatever's in front of psi 1 up here at that initial time. So it looks like 2a is what's in front of psi 1, right? Psi 1 already has the root 2 over a in it. So whatever the coefficient is, which is 2a, that's 2 over root 13 is C1. And so when I square that, I get 4/13 for the probability. Oh, that would be for E1, right? E2 is going to be 3 times A, or 3 over root 13. And when I take the magnitude squared of that, I get 9/13. I'm not sure. There's something doesn't add up here with what I've written down here. I'm asking for the probability that the energy yields E2. So I should be calculating the magnitude of C2 squared there, right? Which is 9/13, not 4/13. That's just me answering the wrong problem there. So pay no attention to the man behind the curtain. It should say 9/13 there. And oh, I see. It's just a typo. I should have written this one as E1. I meant this to be an E1 right there, but instead I copied and pasted and I forgot to change it when I was doing that. So this is supposed to be the probability of measuring E1, probability of measuring E2. And the second one, I'm not sure why. Oh, no, maybe they are supposed to be E2. So this should be really 9/13. If I'm reading correctly. Does everybody agree that if we're talking about the probability of measuring E2, we should take the magnitude of C2 squared, and this should be 9/13 at time t equals 0. Part of the point of doing this worksheet is I'm asking you in C something we've never really talked about before. What about at a later time? That was at t equals 0, right? At t equals 0, we had already done the expansion. In fact, the expansion was given to us at the start of the problem. So we could read off what the C's were once we had normalized it. Now we're asked at some later time, t equals 2 seconds, what's the probability of measuring it for E2? And at a later time, we know how to form what psi is at that later time, right? All I do is put in T2 in there, right? So I can think of this coefficient right here is the C1 that's required at time t equals 0. And once I put in this time-dependent factor, this whole thing is the C1, a complex C1 that changes as time goes on. Okay, so this tells me what C1 is at some later time. So we could call that C1 as a function of t. Similarly, the coefficient of psi2 at a later time would be this number. That's C2 as a function of time. And so if I literally take this, the question literally, we're talking about E2, when I should be calculating the magnitude of C2 of t squared, and that would be, 3 over root 13 times the positive exponential times 3 over root 13 times the negative exponential, just multiplying C star times C. And of course, those exponentials cancel against each other, and I get the same number I did before. The answer should be 9/13. Or I should be asking about E1, and then the work that's shown is correct. I'm not sure. That's not corrected on your worksheet, is it? Does it say E2 on there? Yeah, so this should be 9/13 and this should be 9/13 as written, but the gist of it goes there. For some reason, I went into E1 mode when I was writing my solution. Okay, any questions about how to do it at later times, right? So when we put in those time-dependent factors to get the time-dependent wave function, the coefficients now have some time dependence because we're still looking for what is the coefficient of each one of these lowercase psi's. And this stuff makes the coefficient change with time, but in a trivial way so that the energy probabilities don't change as time goes on. Now, I know none of you got to D, but let's just read and think about D together. Find the probability that measurement of the particle's position at time t yields a number between a over 4, that's somewhere in the well, and a over 4 plus dx. And that sounds a little bit strange, but if you remember back when we first started talking about probabilities, we said rho of x, one way to think about rho of x is the probability of a position measurement between x and x plus dx. So it's like we're talking about rho. In this case, we want rho of x evaluated at x equals a over 4, right? That would tell me the probability of being between a over 4 and a over 4 plus dx. And all that means is I want to substitute in, right? How do I calculate that probability? I just multiply rho times dx. So I'm sorry, rho of x, I misspoke there. Rho of x times dx is the probability of being between x and x plus dx, and that's the thing we integrate. Okay, so here, this probability, this probability is the rho of x, which we know how to calculate, times dx, and we want to evaluate rho of x at a over 4 if we want to find the probability in that little range, sort of an infinitesimal range. We're just saying, let's take a tiny region centered on a over 4 on the x-axis, and let's see how that tiny little probability, it'll be tiny because it's proportional to dx, right? It's going to be a tiny probability, but we want to see how it goes up and down with time. Okay, we can just work out the details. I have to plug in x equals a over 4 into this sum of two, states wave function. We plug in x equals a over 4, and then FOIL it out or multiply it out with all the time dependence in there and simplify, right? The complex exponentials cancel for the first term and the last term, but they don't cancel for the outer and inner terms when we do that. And so when I simplify this magnitude of psi squared there, it just gives me a number. Magnitude of psi 2 squared at a over 4 times this constant gives me another number. This stuff here looks like kind of a mess, but I could simplify it into e to the I t over h bar times parentheses e1 minus e2. And this one in the fourth term right here, it has exactly the negative of that exponent. I could write it as e to the I, or e to the minus I, t over h bar times e1 minus e2. And then I've got a sum of two exponential functions with differing signs. That looks like a cosine. Remember, e to the I theta plus e to the minus I theta over 2 is cosine. So the sum of those two is 2 times the cosine. And I've worked that into this constant here. So this cosine depends on time. And what that means is the probability of being found at this location is a constant plus a sinusoidal up and down value, right? So as time goes on, if we look at position a over 4 on the x-axis and we say, what's the probability of being found in a little narrow region there? It's going to be a constant plus a function that goes up and down sinusoidally, like a cosine function with t. So it's just going to ride up and down as time goes on. This is just one way to kind of interpret that, because it looks like a little bit of a mess before you pull that cosine out, right? You look at this and you say, how do I think about that time dependence? But luckily we have Euler's formula and we can convert it into this form. So remember that. It may appear in a homework problem that's coming up somewhere in chapter 2. I have a vague memory of that. Okay, any questions on that? I think there was a voting question back here that I just skipped over and we're not going to do it, but here it was a follow-on to the previous one. Assuming your system is isolated, does the probability of measuring E1 depend on time of the measurement? And the answer is no. C1 of t has a complex exponential part that goes with it. But when I take C1 star times C1, the complex exponential parts cancel each other out, and we get the same answer we do at time t equals 0. Okay, I think that is the end of the chapter section 2.2 material. Let's just click forward and make sure there's nothing else here. No, I'm not expecting that to be there. Did I not save my slides? I don't know. But in any case, not showing what I'm expecting to be seeing based on how I adjusted it this morning. But let's talk about 2.3. So any questions before we go on and talk about the harmonic oscillator? We'll just kind of set it up and we won't really do the detailed work because we got less than 10 minutes left today. And I was thinking some of this intro stuff was going to be on the slides, but I don't see it on there, so I'm just going to do it on the board. So one thing that's nice about, I'm on page 30 of the notes if you're following along. The nice thing about the infinite square well is that the math works out easily. We get nice intuitive functions. They're sines of n pi x, and then they go to 0. So they're easy to understand. They're pretty easy to integrate, but it's not very realistic. You know, we don't normally encounter potentials that suddenly go to infinity, right? Infinitely hard brick walls or something like that. That's not a usual potential. So a more realistic potential we expect to be nice and smooth. V as a function of x. Again, we're not considering time-dependent potentials. So these potentials we're imagining, you know, might vary smoothly like this. And, you know, if you're interested in the behavior of something near any in one small location, you might say, well, relative to the bottom of this valley here, if I work at it, I can fit a parabola perfectly in the bottom of that. So if I'm only interested in how the potential behaves in a small region here, I could use the appropriate harmonic oscillator potential, 1/2 kx squared, right? What we think of as mass on a spring, but here we're just thinking of it as a quadratic potential function. If I'm only interested in this small region, there's another parabola that works, and so on. And so we can think of the importance of a quadratic potential as it's sort of a good approximation to any smooth potential when you're close to the bottom of the local part of the potential, right? Hopefully you talked about that in mechanics, advanced mechanics. Okay, now, so we're just, you know, at any point we're going to say, well, you know, if this is the parabola we're interested in, we're going to recenter it to 0. So the kind of function we are really interested in here, v of x as a function of x, we're going to take our parabola of interest to be centered at the origin like that. So that's our potential energy function. And we know from introductory physics, it might be something like 1/2 kx squared, where k is the spring constant if we're thinking of a mass attached to a spring. If you look in Griffiths, he doesn't write it this way. And it's not surprising because there's, you know, down at the quantum mechanical level, these forces are maybe generated by electron repulsions or something like that, right? You put an electron between two other electrons, it doesn't like to get near its neighbors, so the potential energy goes up as you go to either side. There's no springs, and so it's hard to think about the spring constant. Instead, you know from your introductory physics and probably advanced mechanics too, that the harmonic oscillation frequency, the angular frequency, omega, is related to k and m. It's root k over m. So I could solve this relation for k and substitute it in there, and that's what Griffiths does. When you do that, you get 1/2 m omega squared x squared. Okay, that's the same as 1/2 kx squared. We just traded out a spring constant, which is kind of unintuitive, for the harmonic oscillation frequency of such a mass spring system. Okay, and so our goal, as always, just like when we started out before, we're going to try to solve the time-independent Schrodinger equation with this potential. Let's just write down the whole thing. Minus h bar squared over 2m. Remember, it's an ordinary differential equation for a function of one variable, right? That's what ordinary means. That's the kinetic energy operator applied to psi plus the potential energy operator, and our potential energy operator is 1/2 m omega squared x squared applied to psi, should be equal to E psi. And we're going to look for solutions to this ordinary differential equation, psi is a function of x, that are normalizable. They can't like go up to plus or minus infinity or something like that as you go out on the x-axis. Now, there are two approaches, and I'm assuming you guys talked about at least the answer to this in modern physics, and there are two ways to approach it. You can either treat it as a differential equation, or there's an easier method, at least for the harmonic oscillator, that's called the algebraic method, and I'm assuming you did not talk about that. Maybe you didn't talk about either of them, but you remember something about the ENs being n plus 1/2 times h bar omega, right? 1/2 h bar omega, 3/2 h bar. So, you know, you probably emphasize just the solutions, but not the method of the solution. So we're going to be very concerned about how we get to those solutions. Okay, so we're gonna start with the algebraic method. So unlike what we did before, we're not gonna jump in and try to solve this differential equation. We're gonna do something different. So you just gotta kind of hold your breath, follow along, read the details in Griffiths. The details are also in my notes. So we're gonna be going through them here, but it's a technique for finding what the allowed psi's are and the corresponding allowed e's that you've never seen before in this class. So it's something new. Don't expect it to sound familiar. Okay, so this is what we might call the algebraic method. Okay, we've got our operators. I'm just going to write down the position operator means just multiply by x. When it operates on something that follows it, you just multiply that function by x. The momentum operator, I won't put a little x on it, minus I h bar times the derivative with respect to x. We're going to define in terms of these two new operators. Okay, we're going to define something that's called, at least in Griffiths notation, a plus subscript there. This is called the raising operator. Okay, and sometimes in other books, just so you've seen it before, it's also known as the creation operator. Because it's going to move energy up, so it sort of creates quanta of energy, but don't think of it as too spooky or anything. It's just somehow it's going to raise the energy up or create new energy. Similarly, we're going to define a minus, which is called the lowering operator. And this is also known as the annihilation operator in other books. That's a more common name for it. And together, sometimes people talk about these two operators as the ladder operators. Okay, a lot of different names, but different books have different names, so it's good to just know that all three of those are possibilities. Here's how we're going to define these two operators. So they're defined in terms of momentum and position operators. A, we'll give a formula for both of them at the same time. A plus or minus is equal to this constant, 1 over root 2m h bar omega times minus or plus I p hat plus m omega x hat. So it's just each one of these is just a linear combination of the position and momentum operator. It's a function of x plus a derivative with respect to x with some constants thrown in, right? So a plus goes with the minus sign, a minus goes with the plus sign over there. Okay, and the goal, time's up, so all I can do is mention the goal. The goal is to show that if we have one solution, somehow I can come up with one solution, psi of x, then we'll be able to show that if you apply a plus to psi of x, this whole thing is another solution to the time-independent Schrodinger equation, and it's linearly independent. So it's really it's not just a multiple of this one, it's a totally different solution. And since that now is a solution, when I apply a plus to that combination, I get yet another solution, and I can keep going and going and going and get more and more solutions. And the same thing happens on the minus side. If I apply a minus to psi of x, I get another linearly independent solution that's not the same as this, it's not the same as this, not the same as this, and I can go on doing that to my heart's content. Now we'll find out that, as you know, you can't keep going like that. We're going to find out each of these has different energies. One of them is going to correspond to 1/2 h bar omega energy, then 3/2, then 5/2 h bar omega. We can't keep going down because the energies would keep getting lower and lower. So this is supposed to be sort of going up in energy and going down in energy. There's a lowest state, and we'll talk about why that's true tomorrow. So we'll really delve into the details of the harmonic oscillator tomorrow. If you didn't have a chance to do the reading responses, I know 5 of you did, try to do that before tomorrow's class and I'll maybe incorporate some of them into the class. If anybody wants to stay around and briefly talk about anything, I'm happy to do that too. Homework problems or whatever. But you should start looking at that chapter 2 homework because 1 through 4 is due on Friday.
Very well. Have a good day.
See you, Elvis.